Hi, I'm Dr. Angela Rasmussen in the University of Utah from the Department of Electrical and Computer Engineering. So today I wanted to talk about the differences between a DC and an AC signal. This is something that we need to understand as we move forward in this course. So the goal today is to understand the difference between DC and AC signals. So a DC signal is a direct current signal. It's something that we think of like a battery. An AC signal is going to be a signal that is time varying, and so it will be a sinusoid or a combination of sinusoids. So a signal such as your voice can be modeled and mathematically by a summation of a whole bunch of sinusoids. So let's look at an example such as this one. So we have 5 sine of 10t. So the DC portion of this would be 0 volts. And that is the center point around which this signal oscillates. So this would be, the DC component would be 0, and the AC component is going to be this 5 sine 10t. For this signal, we can see that it is centered around 2 volts. So our DC component of this would be 2 volts, and our AC component of this would be the 4 sine 5t plus 90 degrees. Now this is a very common signal where you're going to see an actual DC level, but around it you're going to see a whole bunch of noise and chaotic signal. So we would say that the DC component of this is, if we had no noise, so 1 volt, and the AC component is going to be the noise, and we would model that as a plus minus 1 volt. And that would be the value from the highest level to the lowest level, where 1 is the average level that is seen on there. So DC would be 1, and then the AC component would be the plus or minus 1 volt. So now we want to actually write this. So to write this, mathematically, we would look at this signal, and we would see that it is centered around 0, and it goes up to 10 and down to minus 10. And so our DC component of this would be 0, and our AC is going to be the sinusoidal signal itself. So this looks like, with this value starting at 0 would be a 1, this would be a cosine, and our omega is going to be found by 2 pi f, where f is going to be 1 over the period. And the period we can see here is going to be the point in time of where this repeats itself. So the time period t would be, in this case, 2 pi over 10. And so the frequency is going to be 10 over 2 pi. And so 5 pi. And so therefore our omega, again, omega is in radians per second, so make sure you understand the units that are being used, where frequency is in hertz. And so omega here is going to be 2 pi times this frequency, which is 5 pi. So we could write that as 10 pi squared, or we could calculate that number out by taking 3.14, squaring it, and that's going to be t. And that would be our answer, is the combination of those. So our signal, which is a voltage Vs, is going to be just 10 cosine 10 pi squared t. And that would be our answer for this first one. For this one, we see that it's actually centered around 3, so our DC component here will be 3, and the AC portion, we see that it goes up by 7 and down by 7 in comparison to our DC value. So our magnitude here would be 7. Again, this looks like a cosine. And our time period again is at 2 pi 10. And so we can use the same value we had up above, which was 10 pi squared t. And so combining these, we would write Vs for this case as 3 plus 7 cosine 10 pi squared t. And that would be our answer to describe mathematically this signal. So here we see the center's around 3. It goes up by 0.25 and down by 0.25. So our DC component would be 3, and our AC component is going to be plus or minus 0.25. So our full signal we would write here is Vs would be 3 plus or minus 0.25. And that would be our answer in describing these signals. One other thing to remember from writing signals is when we have a phase shift. A phase shift, the equation was delta t times 2 pi over the time period t. If in comparison to our input signal, comparing it to an output signal, to write the output signal, we want to compare it to that input signal. If it's not shown, that would mean that we would be comparing it at time equals 0 means that our input signal has been put into the system. So we would compare the peak value shift from that point. And so if our output is to the right of our input, we consider this a lag, and we consider that a negative value in this phase shift. If it is to the right or to the left, we say that the output signal leads the input signal, and we would say that this is a plus. So here we see that we have our peak of our output signal is also a peak at time equals 0. So we will not have a phase shift for this example. So there will be no phase shift. And again, we write the time period t to find omega, and that value is hard to read here, but that is actually 0.31 seconds. And that was I got that from a measurement on an oscilloscope, so that would be 0.31. And so I can convert that to frequency by 1 over that value, and then omega is 2 pi of that value. And so that is just the 2 pi over 0.31. So there's no phase shift, so our signal, if this is voltage V of t, is 0 for the DC component, and then the amplitude or magnitude is 5 cosine of this 2 pi over 0.31 t, and then plus 0 for the phase shift in volts. And so this would be the mathematical expression for that signal. For this one, again, our peak is at 0, but now we have a DC shift. And looking at that center, we look and see that yes, it is at 7 volts for the DC, and it goes up by 7 and down by 7. The other way to see what that middle point is to take the whole value from peak to peak. So peak to peak would be this distance. You'll also see that notated as PP, meaning peak to peak. So you can take that value and divide it by 2. So in this case, that peak is 7. And then again, we look like we have a cosine. And our time period this time is 1. So our frequency is 1 hertz, and omega is going to be 2 pi times that 1. So we have 2 pi t plus 0. And then our whole signal for this sinusoid is going to be the DC value of 7 plus 7 cosine of 2 pi t in volts. And that would be our answer mathematically to describe this signal. For this one, it's very confusing to see what that midpoint is. So I'm going to say that 8.8 is my peak and 7.2 looks about my peak on the bottom. So to find the DC value here, again, this would be like a peak-to-peak value divided by 2. I'm going to take 8.8 minus 7.2, divide by 2, and that gives me a 0.8. So that will be my DC value. And going from the DC value to the peak is 8, and then it goes down so it goes up by 8 and then down by 8, so plus or minus 8 volts. And this concludes my examples for the DC and AC characteristics. Thank you.